In this lecture, we introduce and develop the concept of independence between events. The general idea is the following. If I tell you that a certain event A has occurred, this will generally change the probability of some other event B. Probabilities will have to be replaced by conditional probabilities. But if the conditional probability turns out to be the same as the unconditional probability, then the occurrence of event A does not carry any useful information on whether event B will occur. In such a case, we say that events A and B are independent. We will develop some intuition about the meaning of independence of two events and introduce an extension, the concept of conditional independence. We will then proceed to define the independence of a collection of more than two events. If for any two of the events in the collection we have independence between them, we will say that we have pairwise independence. But we will see that independence of the entire collection is something different. It involves additional conditions. Finally, we will close with an application in reliability analysis and with a nice puzzle that will serve as a word of caution about putting together probabilistic models.
As an introduction to the main topic of this lecture sequence, let us go through a simple example and on the way review what we have learned so far. The example that we are going to consider involves three tosses of a biased coin. It's a coin that results in heads with probability P. We're going to make this a little more precise, and the coin is biased in the sense that this number P is not necessarily the same as 1/2. We represent this particular probabilistic experiment in terms of a tree that shows us the different stages of the experiment. Each particular branch corresponds to a sequence of possible results in the different stages, and the leaves of this tree correspond to the possible outcomes. The branches of this tree are annotated by certain numbers, and these numbers are to be interpreted appropriately as probabilities or conditional probabilities. So, for example, this number here is interpreted as the probability of heads in the first toss, an event that we denote as H1. This number here is to be interpreted as a conditional probability. It's the conditional probability of obtaining heads in the second toss, given that the first toss resulted in heads. And finally, this number here is to be interpreted as the conditional probability of heads in the third toss, given that the first toss resulted in heads and the second toss also resulted in heads. Let us now continue with some calculations. First, we're going to practice the multiplication rule, which allows us to calculate the probability of a certain outcome. In this case, the outcome of interest is tails, followed by heads, followed by tails. So we're talking about this particular outcome here. According to the multiplication rule, to find the probability of a particular final outcome, we multiply probabilities and conditional probabilities along the path that leads to this particular outcome. So in this case, it's 1 minus p times 1 minus p. Let us now calculate the probability of a certain event. The event of interest is the event that we obtain exactly one head in the three tosses. This is an event that can happen in multiple ways. Here's one possibility where we have a single head. Here's another possibility. And here's a third one. These are the three possible ways that we can have exactly one head, depending on where exactly that single head appears. Is it in the first toss, in the second, or in the third? To find the total probability of this event, we need to add the probability of the different outcomes that correspond to this event. The probability of this outcome is p times 1 minus p squared. The probability of this outcome is what we calculated. It's again p times 1 minus p squared. And the probability of the third one is also p times 1 minus p squared. So the answer is 3p times 1 minus p squared. Notice that each one of the three different ways that this event can happen have the same probability. So these three outcomes are equally likely. finally, let us calculate a conditional probability. And this is essentially the Bayes rule. Suppose that we were told that there was exactly one head. So in particular, the blue event has occurred. And we're interested in the probability that the first toss is heads, which corresponds to this event here. These are all the outcomes in which the first toss is equal to heads. So, given that the blue event happened, what is the probability that the green event happens? You can guess the answer that it should be 1/3. Why is that? Each one of these blue outcomes has the same probability. So when you condition on the blue outcome having happened, the conditional probability of each one of these should be 1/3. So given that the blue outcome happened, there's probability 1/3 that this particular one has happened, and this is the only one that makes the green event happen. But let us see if we can derive this answer in a formal manner. Let's see if we're going to get 1/3. We use the definition of conditional probabilities. The conditional probability is the ratio, first, of the probability that both events happen divided by the probability of the conditioning event, which is the probability of one head. Now, the probability of both events happening, that we have exactly one head and the first toss is heads, this is the intersection of the blue event and the green event, which can happen only in this particular outcome, namely the sequence heads, tails, tails, and has probability p times 1 minus p squared. The denominator is something that we have already calculated. It's 3p times 1 minus p squared, and so the final answer is 1/3, as we had guessed. Let me now make a few comments about this particular example. This particular example is pretty special in the following respect. We have that the probability of H2 heads in the second toss, given that the first one was heads, is equal to P, and the same is true for the conditional probability of heads in the second toss, given that the first one was tails. In other words, our beliefs about what may happen in the second toss remain the same. There's a probability P of obtaining heads, no matter what happens in the first toss. Telling you the result of the first toss doesn't change your beliefs about what may happen and with what probability in the second toss. And if you were to calculate the unconditional probability of heads in the second toss, what you would get using the total probability theorem would be the following. It's probability of heads in the first toss times probability of heads in the second given heads in the first, plus the probability of tails in the first toss times the probability of heads in the second toss given tails in the first. And if you do the algebra, this turns out to be equal to P again. So the unconditional probability of heads in the second toss turns out to be the same as the conditional probabilities. Again, knowing what happened in the first toss doesn't change your beliefs about the second toss, which were associated with this particular probability P. So what we're going to do next is to generalize this special situation by giving a definition of independence of events, and then discuss various properties and concepts associated with independence. In the previous example, we had a model where the result of the first coin toss did not affect the probabilities of what might happen in the second toss. This is a phenomenon that we call independence, and which we now proceed to define. Let us start with the first attempt at a definition. We have an event B that has a certain probability of occurring. We are then told that event A occurred, but suppose that this knowledge does not affect our beliefs about B. in the sense that the conditional probability remains the same as the original unconditional probability. Thus, the occurrence of A provides no new information about B. In such a case, we may say that event B is independent from event A. If this is indeed the case, notice that the probability that both A and B occur, which is always equal by the multiplication rule to the probability of A times the conditional probability of B given A. So this is a relation that's always true, but if we also have this additional condition, then this simplifies to the probability of A times the probability of B. So we can find the probability of both events happening by just multiplying their individual probabilities. It turns out that this relation is a cleaner way of defining formally the notion of independence. So we will say that two events A and B are independent if this relation holds. Why do we use this definition rather than the original one? This formal definition has several advantages. First, it is consistent with the earlier definition. If this equality is true, then the conditional probability of event B given A, which is the ratio of this divided by that, will be equal to the probability of B. So if this relation holds, then this relation will also hold, and so this more formal definition is consistent with our earlier intuitive definition. A more important reason is that this formal definition is symmetric with respect to the roles of A and B. So instead of saying that B is independent from A, based on this definition, we can now say that events A and B are independent of each other. And in addition, since this definition is symmetric and since it implies this condition, it must also imply the symmetrical relation, namely that the conditional probability of A given B is the same as the unconditional probability of A. Finally, on the technical side, conditional probabilities are only defined when the conditioning event has non-zero probability. So this original definition would only make sense in those cases where the probability of the event A would be non-zero. In contrast, this new definition makes sense even when we are dealing with zero probability events. So this definition is indeed more general, and this also makes it more elegant. Let us now build some understanding of what independence really is. Suppose that we have two events, A and B, both of which have positive probability. And furthermore, these two events are disjoint. They do not have any common elements. Are these two events independent? Let us check the definition. The probability that both A and B occur is 0 because the two events are disjoint. They cannot happen together. On the other hand, the probability of A times the probability of B is positive, since each one of the two terms is positive, and therefore these two expressions are different from each other, and therefore this equality that's required by the definition of independence does not hold. The conclusion is that these two events are not independent. In fact, intuitively, these two events are as dependent as Siamese twins. If you know that A occurred, then you are sure that B did not occur. So the occurrence of A tells you a lot about the occurrence or non-occurrence of B. So we see that being independent is something completely different from being disjoint. Independence is a relation about information. It is important to always keep in mind the intuitive meaning of independence. Two events are independent if the occurrence of one event does not change our beliefs about the other. It does not affect the probability that the other event also occurs. When do we have independence in the real world?
The typical case is when the occurrence or non-occurrence of each of the two events A and B is determined by two physically distinct and non-interacting processes. For example, whether my coin results in heads and whether it will be snowing on New Year's Day are two events that should be modeled as independent. But I should also say that there are some cases where independence is less obvious and where it happens through a numerical accident. You can now move on to answer some simple questions where you will have to check for independence using either the mathematical or the intuitive definition. Let us now discuss an interesting fact about independence that should enhance our understanding. Suppose that events A and B are independent. Intuitively, if I tell you that A occurred, this does not change your beliefs as to the likelihood that B will occur. But in that case, this should not change your beliefs as to the likelihood that B will not occur. So A should be independent of B complement. In other words, the occurrence of A tells you nothing about B and therefore tells you nothing about B complement either. This was an intuitive argument that if A and B are independent, then A and B complement are also independent. But let us now verify this intuition through a formal proof. The formal proof goes as follows. We have the two events, A and B, and event A can be broken down into two pieces. One piece is the intersection of A with B, so that's the first piece. And the second piece is the part of A which is outside B, and that piece is A intersection with the complement of B. So these are the two pieces that together comprise event A. Now these two pieces are disjoint from each other, and therefore by the additivity axiom, the probability of A is equal to the probability of A intersection B plus the probability of A intersection with B complement. Using independence, the first term becomes probability of A times probability of B, and we leave the second term as is. Now let us move this term to the other side, and we obtain that the probability of A intersection with B complement is the probability of A minus the probability of A times the probability of B. We factor out the term probability of A, and we are left with 1 minus probability of B. And then we recognize that 1 minus the probability of B is the same as the probability of B complement. So we proved that the probability of A and B complement occurring together is the product of their individual probabilities, and that's exactly the definition of A being independent from B complement, and this concludes the formal proof. Conditional probabilities are like ordinary probabilities, except that they apply to a new situation where some additional information is available. For this reason, any concept relevant to probability models has a counterpart that applies to conditional probability models. In this spirit, we can define a notion of conditional independence, which is nothing but the notion of independence applied to a conditional model. Let us be more specific. Suppose that we have a probability model and two events, A and B. We are then told that event C occurred, and we construct a conditional model. Conditional independence is defined as ordinary independence, but with respect to the conditional probabilities. To be more precise, remember that independence is defined in terms of this relation, that the probability of two events happening is the product of the probabilities that one of them is happening times the probability that the other one is happening. This is the definition of independence in the original unconditional model. Now, in the conditional model,
We just use the same relation, but with conditional probabilities instead of ordinary probabilities. So this is the definition of conditional independence. We may now ask, is there a relation between independence and conditional independence? Does one imply the other? Let us look at an example. Suppose that we have two events, and these two events are independent. We then condition on another event C, and suppose that the picture is like the one shown here. Are A and B conditionally independent? Well, in the new universe where C has happened, events A and B have no intersection. As we discussed earlier, this means that events A and B are extremely dependent. Within C, if A occurs, this tells us that B did not occur. The conclusion from this example is that independence does not imply conditional independence. So in this particular example, we saw that the answer here is no. Given C, A and B are not independent. We have already seen an example in which we have two events that are independent but become dependent in a conditional model. So that dependence and unconditional independence is not the same. We will now see another example in which a similar situation is obtained. The example is as follows. We have two possible coins, coin A and coin B. This is the model of the world given that coin A has been chosen. So this is a conditional model given that we have in our hands coin A. In this conditional model, the probability of heads is 0.9, and moreover, the probability of heads is 0.9 in the second toss, no matter what happened in the first toss, and so on as we continue. So given a particular coin, we assume that we have independent tosses. This is another way of saying that we're assuming conditional independence. Within this conditional model, coin flips are independent. And the same assumption is made in the other possible conditional universe. This is a universe in which we're dealing with coin B. Once more, we have conditionally independent tosses, and this time the probability of heads at each toss is 0.1. Suppose now that we choose one of the two coins. Each coin is chosen with the same probability, 0.5. So we're equally likely to obtain this coin and then start flipping it over and over, or that coin and start flipping it over and over. The question we will try to answer is whether the coin tosses are independent. And by this we mean a question that refers to the overall model. In this general model, are the different coin tosses independent, where you do not know ahead of time which coin is going to be? We can approach this question by trying to compare conditional and unconditional probabilities. That's what independence is about. Independence is about certain conditional probabilities being the same as the unconditional probabilities. So this comparison here is essentially the question of whether the 11th coin toss is dependent or independent from what happened in the first 10 coin tosses. Let us calculate these probabilities. For this one, we use the total probability theorem. There's a certain probability that we have coin A, and then we have the probability of heads in the 11th toss, given that it was coin A. There's also a certain probability that it's coin B, and then a conditional probability that we obtain heads, given that it was coin B. We use the numbers that are given in this example. We have 0.5 probability of obtaining a particular coin, 0.9 probability of heads for coin A, 0.5 probability that it's coin B, and 0.1 probability of heads if it is indeed coin B. We do the arithmetic and we find that the answer is 0.5, which makes perfect sense. We have coins with different biases, but the average bias is 0.5. If we do not know which coin it's going to be, the average bias is going to be 0.5. So the probability of heads in any particular toss is 0.5 if we do not know which coin it is. Suppose now that someone told you that the first 10 tosses were heads. Will this affect your beliefs about what's going to happen in the 11th toss? We can calculate this quantity using the definition of conditional probabilities or the Bayes rule, but let us instead think intuitively. If it is coin B, the event of 10 heads in a row is extremely unlikely. So if I see 10 heads in a row, then I should conclude that there is almost certainty that I'm dealing with coin A. So the information that I'm given tells me that I'm extremely likely to be dealing with coin A, so we might as well condition on this equivalent information that it is coin A that I'm dealing with. But if it is coin A, then the probability of heads is going to be equal to 0.9. So the conditional probability is quite different from the unconditional probability, and therefore information on the first 10 tosses affects my beliefs about what's going to happen in the 11th toss, and therefore we do not have independence between the different tosses. Suppose I have a fair coin which I toss multiple times. I want to model a situation where the results of previous flips do not affect my beliefs about the likelihood of heads in the next flip. And I would like to describe this situation by saying that the coin tosses are independent. You may say, we already defined the notion of independent events. Doesn't this notion apply? Well, not quite. We defined independence of two events, but here we want to talk about independence of a collection of events. For example, we would like to say that the events heads in the first toss, heads in the second toss, heads in the third toss, and so on, are all independent. What is the right definition? Let us start with the intuition. We will say that a family of events are independent if knowledge about some of the events does not change my beliefs, my probability model for the remaining events. For example, if I want to say that events A1, A2, and so on are independent, I would like relations such as the following to be true. The probability that event A3 happened and event A4 does not happen remains the same even if I condition on some information about some other events. Let's say if I tell you that A1 happened or that both A2 happened and A5 did not happen. The important thing to notice here is that the indices involved in the event of interest are distinct from the indices associated with the events on which I'm given some information. I'm given some information about events A1, A2, and A5, what happens to them, and this information does not affect my beliefs about something that has to do with events A3 and A4. I would like all relations of this kind to be true. This could be one possible definition, just saying that a family of events are independent if and only if any relation of this type is true. But such a definition would not be aesthetically pleasing. Instead, we introduce the following definition, which mimics or parallels our earlier definition of independence of two events. we will say that a collection of events are independent if you can calculate probabilities of intersections of these events by multiplying individual probabilities. And this should be possible for all choices of indices involved and for any number of events involved. Let us translate this into something concrete. Consider the case of three events, A1, A2, and A3. Our definition requires that we can calculate the probability of the intersection of two events by multiplying individual probabilities. And we would like all these three relations to be true, because this property should be true for any choice of the indices. What do we have here? This relation tells us that A1 and A2 are independent. This relation tells us that A1 and A3 are independent. This relation tells us that A2 and A3 are independent. We call this situation pairwise independence. But the definition requires something more. It requires that the probability of three-way intersections can also be calculated the same way by multiplying individual probabilities. And this additional condition does make a difference, as we're going to see in a later example. Is this the right definition? Yes. One can prove formally that if the conditions in this definition are satisfied, then any formula of this kind is true. In particular, we also have relations such as the following. The probability of event A3 is the same as the probability of event A3 given that A1 and A2 occurred, or the probability of A3 given that A1 occurred but A2 didn't. Or we can continue similarly, the probability of A3 given that A1 did not occur and A2 occurred, and so on. So any kind of information that I might give you about events A1 and A2, which one of them occurred and which one didn't, is not going to affect my beliefs about event A3. The conditional probabilities are going to be the same as the unconditional probabilities. I told you that this definition implies that all relations of this kind is true. This can be proved. The proof is a bit tedious, and we will not go through it. We will now consider an example that illustrates the difference between the notion of independence of a collection of events and the notion of pairwise independence within that collection. The model is simple. We have a fair coin, which we flip twice. So at each flip, there is probability 1/2 of obtaining heads. Furthermore, we assume that the two flips are independent of each other. Let H1 be the event that the first coin toss resulted in heads, which corresponds to this event in this diagram. Let H2 be the event that the second toss resulted in heads, which is this event in the diagram. The two ways that we can have the second toss being heads. Now, we're assuming that the tosses are independent. So the event heads has a probability which is equal to the probability that the first toss resulted in heads, that's 1/2, times the probability that the second toss resulted in heads, which is 1/2, so the product is 1/4. We have probability 1/4 for this outcome. Now the total probability of event H1 is 1/2, which means that the probability of what remains should be 1/4, so that the sum of these two numbers is 1/2. By the same argument, the probability of this outcome, tails heads, should be 1/4. We have a total of 3/4, so what's left is 1/4, and that's going to be the probability of the outcome tails. Let us now introduce a new event, namely the event that the two tosses had the same result. So this is the event that we obtain either heads-heads or tails-tails. Schematically, event C corresponds to this blue region in the diagram. Is event C independent from the events H1 and H2? Let us first look for pairwise independence. Let's look at the probability that H1 occurs and C occurs as well. So the first toss resulted in heads and the two tosses had the same result. So this is the same as the probability of obtaining heads followed by heads. And this corresponds to just this outcome that has probability 1/4. How about the products of the probabilities of H1 and of C? Is it the same? Well, the probability of H1 is 1/2. And the probability of C, what is it? Event C consists of two outcomes. Each one of these outcomes has probability 1/4, so the total is again 1/2. And therefore, the product of these probabilities is 1/4. So we notice that the probability of the two events happening is the same as the product of their individual probabilities, and therefore H1 and C are independent events. By the same argument, H2 and C are going to be independent. It's a symmetrical situation. H1 and H2 are also independent from each other. So we have all the conditions for pairwise independence. Let us now check whether we have independence. To check for independence, we need to also look into the probability of all three events happening and see whether it is equal to the product of the individual probabilities. So the probability of all three events happening, this is the probability that H1 occurs and H2 occurs and C occurs. What is this event? Heads in the first toss, heads in the second toss, and the two tosses are the same. This happens if and only if the outcome is heads followed by heads, and this has probability 1/4. On the other hand, if we calculate the probability of H1 times the probability of H2 times the probability of C, we get 1/2 times 1/2 times 1/2, which is 1/8. These two numbers are different, and therefore one of the conditions that we had for independence is violated. So in this example, H1, H2 and C are pairwise independent, but they are not independent in the sense of an independent collection of events. How are we to understand this intuitively? If I tell you that event H1 occurred, and I ask you for the conditional probability of C given that H1, what is this? This is the probability that we obtain, given that the first event is heads, the first result is heads, the only way that you can have the two tosses having the same result is going to be if the second toss also results in heads. And since H2 and H1 are independent, this is just the probability that we have heads in the second toss, and this number is 1/2. And 1/2 is also the same as the probability of C. That's another way of understanding the independence of H1 and C. Given that the first toss resulted in heads, this does not help you in any way in guessing whether the two tosses will have the same result or not. The first one was heads, but the second one could be either heads or tails with equal probability. So, event H1 does not carry any useful information about the occurrence or non-occurrence of event C. On the other hand, if I were to tell you that both events H1 and H2 happened, what would the conditional probability of C be? If both H1 and H2 occur, then the results of the two coin tosses were identical, so you know that C also occurred, so this probability is equal to 1. And this number 1 is different than from the unconditional probability of C, which is 1/2. So we have here a situation where knowledge of H1 having occurred does not help you in making a better guess on whether C is going to occur. H1 by itself does not carry any useful information. But the two events together, H1 and H2, do carry useful information about C. Once you know that H1 and H2 occurred, then C is certain to occur. So your original probability for C, which was 1/2, now gets revised to a value of 1. So H1 and H2 carry information relevant to C, and therefore C is not independent from these two events collectively, and we say that events H1, H2, and C are not independent. Independence is a very useful property. Whenever it is true, we can break up complicated situations into simpler ones. In particular, we can do separate calculations for each piece of a given model and then combine the results. We're going to look at an application of this idea into the analysis of reliability of a system that consists of independent units. So we have a system that consists of a number, let's say n of units, and each one of the units can be up or down, and it's going to be up with a certain probability pi. Furthermore, we will assume that unit failures are independent. Intuitively, what we mean is that failure of some of the units does not affect the probability that some of the other units will fail. If we want to be more formal, we might proceed as follows. We could define an event ui to be the event that the ith unit is up, and then make the assumption that the events u1, u2, and so on up to un, if we have n units, are independent. Alternatively, we could define events fi, where event fi is the event that the ith unit is down, or that it has failed. And we could assume that the events fi are independent, but we do not really need a separate assumption. As a consequence of the assumption that the ui's are independent, one can argue that the fi's are also independent. How do we know that this is the case? If we were dealing with just two units, then this is a fact that we have already proved a little earlier. We did prove that if two events are independent, then their complements are also independent. Now that we're dealing with multiple events here, a general number n, how do we argue? One approach would be to be formal and start from the definition of independence of the u events, and that definition gives us a number of formulas, then manipulate those formulas to prove the conditions that are required in order to check that the events fi are independent. This is certainly possible, although it is a bit tedious. However, the approach we will be taking in situations like this one is that we will use the intuitive understanding that we have of what independence means. So independence in this context means that whether some units are up or down does not change the probabilities that some of the other units will be up or down. And by taking that interpretation, independence of the events that units are up is essentially the same as independence on the units have failed. So we take this implication for granted, and now we move to do some calculations for specific systems. Consider a particular system that consists of three components, and we will say that the system is up if there exists a path from the left to the right that consists of units that are up. So in this case, for the system to be up, we need all three components to be up, and we proceed as follows. The probability that the system is up, this is the event that the first unit is up, and the second unit is up, and the third unit is up. And now we use independence to argue that this is equal to the probability that the first unit is up times the probability that the second unit is up times the probability that the third unit is up. And in the notation that we have introduced, this is just P1 times P2 times P3. Now let us consider a different system. In this system, we will say that the system is up, again, if there exists a path from the left to the right that consists of units that are up. In this particular case, the system will be up as long as at least one of those three components are up. We would like, again, to calculate the probability that the system is up. And the system will be up as long as either unit 1 is up, or unit 2 is up, or unit 3 is up. How do we continue from here? We cannot use independence readily because independence refers to probabilities of intersection of events, whereas here we have a union. How do we turn a union into an intersection? This is what De Morgan's laws allow us to do, and involves taking complements. Instead of using formally De Morgan's laws, let's just argue directly. Let us look at this event, that unit 1 fails, and unit 2 fails, and unit 3 fails. What is the relation between this event and the event that we have here? They are complements. Why is that? Either all units fail, which is this event, or there exists at least one unit which is up. So, since this event is the complement of that event, this means that their probabilities must add to 1, and therefore we have this relation. And now we're in better shape because we can use the independence of the events f to write this as the 1 minus the product of the probabilities that each one of the units fails. And with the notation that we have introduced using the PIs, this is as follows. The probability that unit 1 fails is 1 minus the probability that it is up. Similarly, for the second unit, 1 minus the probability that it is up, and the same for the third unit. So we have derived a formula that tells us the reliability, the probability that a system of this kind is up, in terms of the probabilities of each individual components. You will have an opportunity to deal with more examples of this kind, a little more complicated in the problem that follows, and even more complicated in one of the problem-solving videos that we will have available for you. Let us now conclude with a fun problem, which is also a little bit of a puzzle. We are told that the king comes from a family of 2 children. What is the probability that his sibling is female? Well, the problem is too loosely stated, so we need to start by making some assumptions. First, let us assume that we are dealing with an anachronistic kingdom where boys have precedence. In other words, if the royal family has 2 children, one of which is a boy and one is a girl, it is always the boy who becomes king, even if the girl was born first. Let us also assume that when a child is born, it has 50% probability of being a boy and 50% probability of being a girl. And in addition, let's assume that different children are independent as far as their gender is concerned. Okay, given these assumptions, perhaps we can argue as follows. The king's sibling is a child which is independent from the king. Its gender is independent from the king's gender. So it's going to be a girl with probability 1/2. And so this is one possible answer to this problem. Is this a correct answer? Well, let's see. We have to make a more precise model, so let's go ahead with it. We have two children, so there are 4 possible outcomes. Boy, 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 girl, girl, boy, and girl, girl. Each one of these outcomes has probability 1/4 according to our assumptions. For example, the probability of a boy followed by a boy is 1/2 times 1/2, where we're also using independence. So each one of these 4 outcomes has the same probability, 1/4. Now, we know that there is a king, so there must be at least one boy. Given this information, one of the outcomes becomes impossible, namely the outcome girl-girl, and we're restricted to a smaller universe with only 3 possible outcomes. Our new universe is this green universe, which includes all outcomes that have at least one boy so that we can get a king. We should therefore use the conditional probabilities that are appropriate to this new universe. Since these 3 outcomes inside the green set have equal unconditional probabilities, they should also have equal conditional probabilities. So each one of these 3 outcomes should have a conditional probability equal to 1/3. In 2 of these outcomes, the sibling is a girl, and therefore the conditional probability, given that there is a king and therefore given that there is a boy, the conditional probability is going to be 2/3. So this is actually the official answer to this problem, and this answer is incorrect. Are we satisfied with this answer? Maybe yes, maybe no. Actually, some more assumptions are needed in order to say that 2/3 is the correct answer. Let me state what these assumptions are. We assume that the royal family decided to have exactly 2 children. So the number 2 that we have here is not random. It was something that was predetermined. Once they decided to have the 2 children, they had them. At least one turned out to be a boy, and that boy became a king. Under this situation, indeed, the probability that the sibling of the king is female is 2/3. But these assumptions that I just stated are not the only possible ones. Let's consider some alternative assumptions. For example, suppose that the royal family operated as follows. They decided to have children until they get one boy. What does this tell us? Well, since they had 2 children, this tells us something that the first child was a girl. So in this case, the probability that the king's sibling is a girl is equal to 1. The only reason why they had 2 children was because the first was a girl and then the second was a boy. Suppose that the royal family made some different choices. They decided to have children until they would get 2 boys, just to be sure that the line of succession was secured. In this case, if we are told that there are only 2 children, this means that there were exactly 2 boys, because if one of the 2 children was a girl, the royal family would have continued. So in this particular case, the probability that the sibling is a girl is equal to 0. And you can think of other scenarios as well that might give you different answers. So 2/3 is the official answer as long as we make the precise assumptions that the number of children, the number 2, was predetermined before anything else happened. The general moral from this story is that when we deal with situations that are described in words somewhat vaguely, we must be very careful to state whatever assumptions are being made, and that needs to be done before we are able to fix a particular probabilistic model. This process of modeling will always be something of an art in which judgment calls will have to be made.